Hello, my students. Here I am, finally back. My life has been very busy recently, and it's about to get busier. So we will get through the end of the semester for what you need. It will be all okay. All right, so I wanted to go back over your quiz answers with you. This set of quiz answers, I'm not sure if it's because I got you the wrong notes the first time or what happened, but they seemed a little more rushed, a little less prepared to me. So up until now, I've given you an A for each quiz. This time I'm giving you guys a B. So I'm going to go through the answers so that we can make sure you understand what I was looking for. You did well with some of it and not as well with each other ones, and each of you did well on some of it, and each of you did not as well on some of it, so it's a B, but that's okay. You're probably getting an A in this class. I don't know, but I know you can do well. So let's do some review here on what was going on with the quiz. So with the set one, we were talking about ions, anions, cations. Did well with the answer for what is an ion, anion, cation. For number two, oxidation reduction, that was a little rushed. The main thing I want you to understand is that oxidation reduction are processes. So it's the process of gaining electrons, or it's the process of losing electrons. So make sure you understand an anion is a thing and oxidation reduction is a process. I could kind of hear that in Salman's response, but it felt a little rushed. And that's kind of how it went for each one that didn't go well. So it's not just Salman, it was everybody did this. All right, NGEC. I was looking for an explanation. Noble gas electron configuration, you got that right, Ina, but what does it mean? So let's think about that for a second, all right? So let's say I've got an atom and there's the nucleus with its neutrons and protons, and then we've got the electrons on the outside. The first level of the first ring of electrons outside of that will only have 2 electrons, but beyond that, each layer can have up to 8. And when it does have 8 like that, that's when it has noble gas electron configuration, because the noble gases all have a full outer ring of electrons. So what's happening when an atom tries to reach noble gas electron configuration is that if it has less than 8, so let's see here. If it has less than 8, so 3, 4, 5, 6, say that it has 6, all right? And then there's some other atom over here. Let's say that it has, I'm not even thinking about what these are, but let's say that this atom has 2 electrons in its outer ring. Let's do it actually for something so we can get up to 8, just so that we're talking about 8s. All right, so let's say this one has 2 extra electrons in its outer ring, and this one is missing. It's got space for 2 electrons. So what will happen is that the electrons from one atom will move to the other, and that will cause this atom over here to become positive because it's lost 2 electrons, and this one will become negative because it's gained 2 electrons. So that's what we mean by noble gas electron configuration. Stoichiometry, be careful. I think the example was Fe2S3. No, what was it? Fe2O3? Yes. So you gave your example kind of quickly, and it showed me that you didn't understand it. So Fe2O3, in Fe2O3 we've got positive 3, and we've got, sorry, I just wrote 6, positive 3. So this is positive 3 iron, the cation positive 3 iron, and negative 2. Oxygen is always negative 2 for an atom because it wants to give up 2 electrons. You wrote a 6 right here. That wouldn't work out stoichiometrically. That wouldn't work out. That would give us the wrong math. So make sure you understand the math of stoichiometry is that if I've got positive 3 times 2 and negative 2 times 3, that this equals positive 6, and this equals -6. I think you were swapping the 6's in here, but that's where it's important, is that this and this balance. They become 0. So yes, make sure you understand stoichiometry. I taught you wrong. I went looking for examples of stoichiometry. I learned this wrong, or I memorized this wrong a very long time ago, like probably 20 years ago. Some minerals are not stoichiometric. I was looking for examples for you and I found it. I was thinking, oh, I'll look at pyrite, and it's not stoichiometric, and it scared me. So FYI, I was wrong. Not all minerals want to become stoichiometric, but most of the time they do. Most of the time they want most things in nature want to be balanced. So positive and negative charges becoming zeroed out inside of the molecule, or inside of the crystal in this case with minerals. So okay, so that's stoichiometry and NGEC, noble gas electron configuration. Types of bonds, you did pretty well on these, so I'm not going to spend too much time on this. Covalent, though, I do want you to understand why. Why does it have such a strong balance, or a strong bond? If one atom and another atom are completely sharing an electron, they both depend upon this electron. They both must have this electron. It's really hard to break those two apart. Those two atoms really want to stay together now that they are sharing an electron. So that's the reason why it's so strong. Did a good job with metallic. Ionic bond, again, this is similar to the NGEC problem. Actually is exactly the same. So let's go back over here. And this right here is an ionic bond. If I've got a +2 here on this atom because it's given up 2 electrons, I have a -2 charge on this atom because it's taken in 2 electrons. Now the charge on this side is positive, and the charge on this side is negative. And that means these atoms are going to be drawn together just like magnets, positive and negative coming together. All right, and van der Waals, you did a good job with that. It's more complicated. It's not, but yes. It's like layers of molecules that get attracted to each other. We're good. That's all good. No worries on that one. Set 3, I was a bit confusing. I'm sorry. That's okay. You guys did okay on that one. Let's see here. What I was hoping that you would do, I wasn't clear, was that you would write the formulas on the board and then tell me what they are. So silicates have Si, and then any number of X's, not any number of X's, but different values of X's. O and different values of oxygen, and then that will produce a specific anion charge. It could be -1, it could be -2, it could be -3, and that will determine what can bond on it on the other side. And then our non-silicates. So you got, question 1, 3, and don't worry, this is okay. It was really my fault. I didn't explain it well. So if I've got O2 negative, what is this? So this is what I was hoping you'd do. These are oxides. I just want you to be able to recognize the names, though I don't think we're really going to get into them. I think all we're going to end up doing is the silicates. But oxides, this is, if it's CO3 -2, this is the carbonates. We don't tend to run into these except in sedimentary rocks, though they can be in igneous rocks, totally can be, but they're what we call accessory minerals, which means they don't happen very often. S2 negative, whoa, sulfides, SO4 -2, sulfates, just so you can recognize the names. PO4 -3, phosphates, Cl, the anion of Cl chloride, the anion of fluoride, the anion of bromide. These are halides. And again, actually I'm looking at most of these, and most of these, I think most of these end up being in our sedimentary minerals. And the native elements, which definitely can be in igneous rocks. That's where we mine most of them, but they can be transported in sedimentary ways. And you got that one just fine. It's gold, copper, silver, da 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 da. All right. So don't worry, I didn't explain what I was looking for. That's okay. Step 4, you guys did pretty well on controls for mineral formation. Did a good job in explaining how time controls mineral formation, that they get larger the longer that they have to grow. Temperature. Salman, you did a really good job on this one. Good job, girl. You did very well on how temperature controls if the atoms are moving quickly because of high temperature, they're not going to bond easily, so they'll make simple structures. We're going to talk more about that today. Chemistry. Then this is the one where we lost Yuampa. So everybody got lost somewhere. All right, so I'll re-explain this one. The reason I talked about the sodium chloride as an example. So sodium chloride is halite, right? And if I have, maybe I just didn't explain it well, but if I have oh my goodness, why are all those popping up? I want them to stop. Let's say I've got a jar with water, and it's got sodium molecules and chloride molecules in it, right? All right. So let's say this is my solution right here, right? And minerals start to form, okay? So the chemistry is going to determine what and how much of each mineral can form. All right? So in this particular scenario, what can I make? I can make sodium chloride. I've got sodium atoms, I've got chloride atoms. So sodium and chloride here, let's say these two pair up and they become sodium chloride. So those are out of the game. And these two pair up and they become sodium chloride. So these are becoming a solid mineral. And these two pair up and they become sodium chloride. All right, so this is going here, this is going here, this is going here. Those are no longer there. Well, I've got 2 more chlorides left. Can I make more sodium chloride? No. Why not? The chemistry is limiting how much more I can make. So if I'm running out of an element, I cannot make any more minerals with that element because I'm out of the ingredient. So I think I could have explained that a little better, but that's what I was looking for. All right, so overall, still you're doing really well. I'm proud of you. I can see on your faces that you understand. It makes me very happy as a teacher to see your faces and see that you understand. So that's really good. Well done. All right, so a little bit more review. Valence. Again, that's just the charge that's on the atom or charge that's on the molecule. Is it an anion? Is it a cation? Is it going positive or negative? NGEC, I've already reviewed that with you. Stoichiometry. Let me do a little bit more review on stoichiometry with you. All right, so let's see. I've got calcium fluoride. This happens to be called fluorite as a mineral, fluorite with a T. So this is made out of calcium and fluoride, and there are 2 fluoride atoms, and there's 1 calcium atom. Let's just skip ahead through those. Let's find out what charge calcium and fluoride have. So calcium tends to have a positive 2 charge. Fluoride tends to have a negative 1 charge. So let's go back. So let's put that positive, oops, why does it keep doing that? Positive 2 charge on that and negative 1 charge on the fluoride. All right, so then, and we know that if we don't have a number down here, that means there's just 1 atom. So I've got 1 atom of positive 2 calcium, and that equals positive 2. And I've got, make sure that doesn't freeze, 2 atoms of negative 1 fluoride, and that equals negative 2. And if I add those together, I've got a 0 charge. So this is a stoichiometric molecule. Fluorite is a stoichiometric mineral. Like I said, I've discovered now that not all minerals are stoichiometric, so I need to go back and change my lectures. And I have lied to many years of students. Teachers do this. We get convinced about something, we teach it, and then we find out that we're wrong. All right, let's do the next one. Al2O3. So let's go back over here and look at aluminum. And aluminum, what charge does aluminum have? It normally has a +3 charge. And oxygen always has a -2 charge. Always. I think I can be confident on that one. It will always lose its 2 outer electrons. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8. Oh, it adds 2 electrons. I'm so sorry. It won't lose its electrons and become positive. It adds 2 electrons and becomes negative. So let's look at this. Why does that happen? Really quickly, let's just use oxygen as an example. All right, so always 2 electrons in the first ring. So 1, 2. So there's, I'm just counting 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's how many electrons it should have, right? Is 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is our example where we've got 2 open spaces readily available for some electrons to fill, all right? And then, I don't really want to comment. Okay, we can do that. Why not? Let's just do it. Yeah, all right, so here's aluminum. 1, 2, so aluminum's at 9, 10, 11, 12. We once upon a time had a teacher that made you memorize the entire periodic table. I don't think you had her, but you might have. If you did, I'm sorry. 13. All right, so 13. So let's get up to that. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're going to go up to the next level. 11, 12, 13. All right, so now I've got, this is aluminum over here. And this is oxygen over here. And it wants 2 electrons. Aluminum, what does it want to do? It wants to give away 3 electrons. All right. So let's go back over here. And we said that this mineral, Al2O3, I'm stumping myself. I can't remember what mineral that's called. It's good. We'll just call it aluminum oxide. We're just going to call it that for now. All right. So it combines 2 aluminum atoms with 3 oxygen atoms. So let's go back over here. So we're saying we're going to have 3 oxygen atoms and 2 aluminum atoms. Why would that be? Well, we've got 3 electrons that it wants to get rid of. So it's got 3 electrons it wants to get rid of. And this one wants 2 electrons. And so how many atoms am I going to need of aluminum versus oxygen? And so if I give away 3 electrons 2 times, and if I gain electrons on the oxygen side 3 times, I don't want to draw this out 3 times, but let's say we've got 3 more electrons here that we're giving away. And here we've got, so we've got, over here we've got 2 atoms of aluminum. Over here we've got 3 atoms of oxygen. And these circles represent holes that want electrons. These arrows represent places where the atom wants to get rid of those electrons. So we can put them all somewhere. So this one's going to go over here, this one's going to go over here, this one's going to go over here, and this one's going to go over here. And now we have happy atoms because these 2 aluminums over on this side have gotten rid of their extra electrons, and they're now at noble gas electron configuration. And these atoms over on the oxygen side have gained electrons to fill these empty spaces, and they are now at noble gas electron configuration, because in both of these scenarios there are now 8 electrons in the outer shells. Woohoo! Happy electrons, not happy electrons, happy atoms, everybody's balanced. Unlike pyrite, which apparently wants to be negative. Don't worry about that. All right, so there we go. Now let's look at one more example of this. I'm totally making a mess here, but let's look at potassium, aluminum, silicon 3, oxygen 8. All right, and let's see what happens here. So what, and this is a type of clay right here. So what happens when we've got potassium? So let's look for potassium first. Potassium has a +1 charge. So let's put a +1 charge here. Aluminum has a +3 charge back over here again. So let's put +3 here. Silicon has a +4 charge. So we're going to put +4 here. And oxygen, again, always has a -2 charge. All right, so let's do the math here. I've got +1. So really, when I add all of these together, I should get to 0. +1 times 1 atom plus +3 times 1 atom plus, I think I'm going to run out of space over here, +4 times 3 atoms plus -2 times 8. So I've got +1 plus +3 plus +12 plus -16. There we go. What am I going to get? I've got all of these together. I'm running out of space. +16 plus -16. And that's going to all equal, I ran out of space, equals 0. There we go. Yay. So this is a stoichiometric mineral, which apparently not all. Yes, most minerals are stoichiometric, always wanting to reach noble gas electron configuration. All right, I wanted to show this video. Well, you know what? I didn't open it up. Since I didn't show it last time, I'm guessing you probably did already look at it, but let's open it up really quickly so that you can check it out. This one right here. Let's watch. I want to talk to you while this is happening. All right, so again, this is a drop of liquid, and what you're seeing is that atoms are being added one row at a time to create a mineral underneath the drop. Let's do that one more time. I wish I could draw on these. But down here at the bottom, atoms are being added out of the liquid where you can't see. It's really interesting. You cannot see the atoms inside of that liquid drop. That liquid drop is just kind of a big ball, right? That you cannot see the atoms in, but you can see as this plays, one atom at a time being added, boom, 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 all around in a circle, creating the mineral underneath it. I think that's fascinating. There you go. So when we're creating minerals, we are adding atoms or groups of atoms, cations and anions, cation groups and anion groups together to create a repeating structure over and over and over again. All right, where are we at? Okay, so I'm going to talk to you about this. It's not going to come up again. This is where one of those places where I was thinking, you know, they don't have to learn this. But it's good for your brains to see how this works, all right? So I want to talk to you a little bit about the unit cell. The unit cell is if you took a mineral and you broke it and you broke it and you broke it until you get to the smallest piece that is still a mineral. It has all of the properties of being a mineral. What would that smallest piece be? It would be called a unit cell. And you could take that unit cell and add another unit cell just like it, and add another unit cell just like it. Have you played with Legos before? think of just the smallest brick, and you put another one and another one and another one, and you keep building with that, and that piece has a specific shape, and if you keep adding more pieces with that shape, you're basically making that shape larger and larger, right? In 3 dimensions. So this is the smallest piece of the mineral that you can repeat again and again. So you can see here, this is creating quartz right here. This is silicon dioxide. So this is my smallest SiO3 that I can get, and interestingly enough, that SiO3, this unit cell, I'm going to say it on the next slide, but it's not the same as the chemical formula. What you see in the unit cell is not represented by the chemical formula. So this is SiO3, even though you can see that there are 5 atoms in it instead of 4. So, don't worry about that. I don't need you to learn all of this. But if I take this and I add 1, 2, 3, 4 of these blocks together, you see that I create the same shape again. And I keep adding them together, and I make larger and larger structures out of that same shape. All right. Inside of the unit cell can be as little as 4 atoms or as many as 1,000. I've read that. I don't know what mineral does that. But, they're all arranged inside of a box, and the atoms can be up on the corners. They can be along an edge here, which I think I've got an example in the next slide that shows that. They can be on a face, which is on the outside of the box, or they can be inside, completely inside the box. Oh no, this one doesn't have any on the edge either. Some of them have ones on the edge like this. Atoms are arranged inside the box. The box has parallel sides. They might not be perfectly cubic. They could be like a rhombohedron. They could, but all the sides are going to be parallel, parallel, parallel. I already said that about the atoms being on the corners, edges, faces. Don't worry about that. And then that box repeats again and again and creates a mineral. So that's a sphalerite unit cell here, and this is sphalerite down here. All right, now some things that will be a little bit more important later, so we're going to pick up learning now. I don't need to install that right now. Paying more attention. All right, so ionic radius. If I take an atom, let's think about this for a little bit. If I take an atom and it's got space, no, let's do it the other way first. Say I've got an atom and it has 2 electrons in its outer ring, right? And so let's find out, what would that be? 2 electrons in its outer ring. Say that it is magnesium, okay? So we've got magnesium. Got magnesium. Do I have magnesium in here in this list? No. Let's find another one that's positive too. Oh, there it is. Yes. So I've got magnesium, right? And it's got, nope, I did this backwards again, didn't I? 2 electrons. Oh no, I did it right. All right. So it's got 2 extra electrons in its outer ring. And what does it want to do? It wants to reach noble gas electron configuration. So it's going to get rid of 2 of those electrons. What will happen to the size of the atom? Will it stay the same? Will it get larger? Or will it get smaller? You can do the math, right? You can figure this out. If I've got an atom and it loses 2 electrons, it will become smaller in size. So cations tend to be smaller than their original atom. The original atom has the electrons that it's supposed to have. The cation has less electrons. It's gotten rid of them, has a positive charge, and it has a smaller diameter, smaller radius. It becomes smaller in size. Let's go the other direction. Oxygen, -2 charge, right? So it's got space for 2 extra electrons. And you're thinking, well, they're on the same ring, right? Well, really, if you add electrons in, the other electrons have to move a little bit to make space for those new electrons. So they don't just move around with 2 holes here. They've been balanced. before, and now those electrons have to move out of the way for new electrons to come in. So if I've got an atom that has opportunity for extra electrons, and it takes extra electrons in, that atom will become larger in size. So anions tend to be larger in radius than their original atom. All right, so ionic radius is the radius of the ion. So we're talking this size from here to there, right? Or from here to here. So in this picture, the gray shows the size of the original atom. The red shows the size of the cation. The blue shows the size of the anion when it becomes ionized. We measure these in angstroms or picometers. So an angstrom, or average ionic radius, is around 1 angstrom or 100 picometers. And 1 angstrom is 1 times 10 to the negative 10th meter. 1 picometer is 1 times 10 to the negative 12th meters. Probably won't too much ask you about exactly this, but I will probably mostly talk about, I think I usually use picometers. So when I'm talking about sizes of anions and cations, we'll be talking in picometers. Ionic radius depends on the atomic number, interaction with other ions. So cations, again, normally have a smaller radius, ionic radius. Anions normally have a larger one. All right, and that will become important because these ions, these cations, these anions can switch out for each other later on. And whether or not they can switch is going to be partially dependent on their size. So we'll come back around to this. All right, so some minerals have a range of chemistry. I kind of want you to understand this because it's going to play into what minerals form during magmatic processes. When magma, melted rock, is cooling, so that's our fluid, it has all these ions in it. It has cations, it has anions. Those cations and anions are connecting together to create minerals, right? And some minerals are very set on their formula. This is the only formula it will ever have. But some minerals are okay with changing out elements. So it could have, well, let's just look at an example. We could look at olivine. Olivine's a great, wonderful beginning example. So you would expect a chemical formula to just have one, the new thing. What is new in this chemical formula? What looks peculiar? What looks strange? What might you not, I don't know, you may have seen this in some other class, but you might not have before, right? It's this comma. What is a comma doing in a chemical formula, right? Why? All right, so let's find out. And then feldspar. Oh, I think, well, we'll get to the explanation why in just a moment. No, I'm going to explain it right now. Why is there a comma? That is the question. The answer is because I can have any combination of magnesium and iron in bulk inside of the atom. Inside of the mineral. All right, so remember, minerals are made out of unit cells. So I could have a unit cell of olivine that has magnesium in it. I could have another unit cell of olivine that has magnesium in it. But then I could have a unit cell of magnesium that has iron in it. And then I can have another unit cell that has magnesium and another one that has magnesium and another one that has iron. And they can all combine together and make olivine. Uh-oh. I don't know what. Oh, because my computer's not plugged in. Hopefully nothing's going to happen. All right. I might have to go plug in a little. All right. So let's say I've got one unit cell. Unit cell of olivine. I'm just going to draw squares, all right? And inside this unit cell of olivine, this one is made out of silicon, oxygen, and magnesium. And next to it is another one made out of silicon, oxygen, and magnesium. But then the next one over is made out of silicon, oxygen, and iron. And then the next one is made out of silicon, oxygen, and iron. And then another one made out of silicon, oxygen, and magnesium. Okay, so this mineral can use magnesium or it can use iron inside of the unit cell. And those unit cells can combine together and it will always make the same mineral. It will have a little different properties though, depending on how much magnesium or how much iron. The color will change, the density will change a little bit because magnesium and iron don't have the same number of neutrons and protons, right? Just an interesting way to do things. All right, feldspar gets a little more complicated. It can have 3 end members. So this is called end members. In olivine, it has 2 end members. It could have 100% magnesium, could have 100% iron, or could have something in the middle. Feldspars could be made with sodium and aluminum, or calcium and aluminum too. And look, everything's changing here. Si2O8, Si3O8, and that's because the charges between these are changing. This would be a great problem if I was giving you homework, which I'm not going to make you do. Maybe I will think on that. This might become part of the quiz. We'll see. And on top of all of that, we could have potassium. That's the plagioclase end. Potassium end is potassium aluminum and Si3O8. All right, so these two are actually kind of similar, but these two make plagioclase, one mineral, and this one makes potassium feldspar, another mineral, and they're all feldspars. If you've studied a little bit of biology, well, I'm not even going to get into all that. This isn't biology, this is geology. All right, so how does this work out? Okay, so again, I could have, let's say, this is Mg, comma, Fe, Si, is it 3 or 2? 2, SiO4. All right. So in this, so let's say I've got a mineral, like the whole thing, not a unit cell. A unit cell would have only magnesium or only iron, but the mineral has a combination of magnesium and iron in it, and somewhere on here, so this could be magnesium on this side, this could be iron on this side, that B should be way over here. And I could have a mineral that's, let's say it's like this, like it has 75% of this option here is magnesium, and that means that 25%, so 75% of that is magnesium and 25% is iron. So I'd write that as magnesium 75, iron 25, 2, SiO4. There we go. Very interesting, right? Or I could have this interesting proposition where I've got 3 different things going on here. So I've got sodium, that should be sodium aluminum. Sodium aluminum, calcium aluminum. I'm probably putting these in the wrong corners. They go in specific corners. And potassium aluminum. And I could have a mineral here, or I could have a mineral here, or here. And depending on how much of each of those end members we have, it'll fall in a different location. All right, these graphs help us to understand something called solid solution. So solid solution is when atoms of similar valence, what do I mean by that? Similar valence. What does valence mean? Valence means charge. So similar charge, so really similar, that's like maybe -1 to -2, or -2 to -3, all right? Or +1 to +2, or +2 to +3. And, whoa, why do we keep zooming in when I put my hand on there? And similar ionic radius, so this is where we're talking in picometers. Most atoms are around, most elements are around 100 picometers, but they can be slightly smaller than that, they can be larger than that. If the size of the atom and the valence, positive or negative, is similar enough, they can switch for each other inside of the atom. Why do I keep doing that? They can switch for each other inside of the mineral. So requirements for a solid solution, a valence difference of only 1. So sodium and calcium have a valence difference of 1. Very simply, they can replace each other according to valence. Magnesium and iron, they're the same, right? Positive 2, very easy for them to switch in and out because they're requiring the same electronic charge valence requirements. They're filling them the same way. The size, though, has to be similar as well. So they have to be within 15%. So let's say if we look at sodium and calcium, why can they, they don't have the same valence. They don't have the same valence. Why can they replace each other? Because their size, their ionic radius, is very, very similar. Much less than 15% difference. So very easy for them to switch. All right, so let's look at these. This is the calcite group. So calcite itself is CaCO3. My undergrad, my diploma project when I was an undergrad had to do with, not this in particular, but I had siderite and calcite and magnesite that I was looking at. So can these elements replace each other? Well, they're based on ionic radius. They can. Calcium has 0.99. Oh, this was in angstroms. Sorry. So it would be 99 picometers or 80 picometers, 74 picometers, 74 picometers. Oh, iron and zinc have the same ionic radius. And magnesium down to 0.66. So that's probably already all centering off of 0.74. All have to be within 15% of 0.74. All right, so we can look again at these sizes. We've got calcium, manganese, iron, zinc, and magnesium. So where's calcium? Calcium, manganese, iron, zinc is not on here, and magnesium. So these are those atoms. And they're all pretty similar. They all have a positive 2 charge, so they can all take each other's place. They can switch inside of that unit cell. They can take a magnesium instead of a calcium, or an iron instead of a manganese. Some substitutions have complete solid solution. This means that it can have from 0 to 100% anywhere in there of those 2 different or 3 different ions. This can happen if the ions are almost equal charge and size. Any mixture can occur. So this is the olivine series. They do have a different name if it's all magnesium or all iron. We'll call it forsterite. I didn't actually learn this in school, but I didn't have to memorize it. So don't worry about it. You don't have to memorize this. Forsterite to phthalate. All magnesium or all iron. But there can be any combination, again, of these two. So I could have like magnesium 10% and iron 90%, 2 of those atoms, and then SiO4. And that's still olivine, complete solid solution anywhere on that line. Plagioclase feldspar, from albite to anorthite, that is one solid solution. And from anorthite to orthoclase is a solid solution. Interestingly enough, albite to orthoclase is not a solid solution. So I can do solid solution having replacement from here all the way down to here. Any combination of calcium dialuminide, or sodium aluminum, or I can go from here to here and replace the sodium and the potassium with one another. They can slide in and out of here. I could have a mineral right there or right here. In this area, they can have all 3. But I cannot outright replace CaAl2 with KAl. I cannot slide between these two. This area is called a miscibility gap. That means that we can't mix within this area the calcium, the sodium, and the potassium. Why is that happening? Let's look at this. Calcium is a positive cation, and it's got an ionic radius of 114 picometers. Sodium is +1. Let's get in here and erase some of this because it's getting hard to see. And so it's +1, it's 116 picometers, so that's definitely really similar. Orthoclase is +1 and 152 picometers. All right, so sodium and calcium here, they have very similar sizes, and they're only off by 1 electron between calcium and sodium. Sodium and potassium have the exact same charge, right? And so it can allow for that larger size of potassium because of that charge being the same. But here, here the charges between calcium and potassium are different, and there's a large difference in size, so these two cannot replace each other. All right. What was I trying to show you here? I'm not sure. Maybe I was going to show you the calcium, and sodium, and potassium. All right. So a big size difference this direction and a different charge. All right, so the miscibility gap, you know what? If I'm having to take a deep breath, you are needing to stand up and stretch. We're almost to the end of this little bit of phase. I'm gonna, how much more do I have? How do I see? There's a way for me to see. I don't remember. Nope, that's not it. Nope, that's not it either. That's not it either. That's not it. Thought there was a way for me to be able to see my... that's all right. Take a break. I'm going to show you my poor puppy while you're taking a break. Stand up, stretch, and look at my poor dog. He had surgery. If you have watched Up, you know what he is wearing. The movie Up, with the house that goes up with the balloons. He's wearing a cone of shame. He feels it. He feels very ashamed. No, really, he just can't scratch himself because he needed surgery. Okay, but he's doing just fine. He's really fine. Oh, he knows I'm talking about him. Hi. Did you notice me talking about you? Do you want to say hi to my students while they're stretching? Hi, Bailey. Here you go. He's doing a good job sleeping. Hopefully he'll go back to sleep. It's very helpful that he's been sleeping. All right. My dog has woken up, and you need to wake up too. Here we go. Continuing on, the miscibility gap. This is the area on the composition diagram where minerals do not form. So minerals do not form inside of this area. No mineral formation. Means that the end members do not mix very easily. Some substitutions involve partial solid solution. So this is usually because we've got ions with different sizes or charges. So we can get some mixture going on there. So calcite, dolomite, and magnesite are 3 carbonates also. And in this case, we can have calcium magnesium with 2 carbonates at the end, or we can have completely magnesium. These are the only combinations that are allowed. About 100% calcium, 50% magnesium, and 50% calcium or 100% magnesium. Can't do 75% calcium and 25% magnesium in this case. So in this case, everything here is possible inside of these. This is calcite up here, this is dolomite, and this is magnesite at the bottom. Everything here is impossible to make. We cannot have, oh, and that's siderite on that end. I didn't put siderite over here. So I can't combine iron and calcium very easily. I can combine calcium and magnesium at 50%. So calcium 50, magnesium 50. Oops, magnesium 50. But otherwise I can't do the combinations here. Feel like I'm taking far too long on this. Why does this happen? Let's see here. Calcium and magnesium and iron, they all have the same charge. Calcium and magnesium are closer in size to one another. Magnesium and iron are very close in size to one another, but magnesium and calcium are very far apart from one another in size, so absolutely no mixing on that side. All right, so calcium, magnesium, and iron. Let's look at those. Calcium there, magnesium there, and iron. Oh, iron's not on this one. That's all right. All right, before we talked about the controls on mineral formation, what are those again? What controls mineral formation? Temperature, time, and chemistry, right? Another one that I didn't talk about before is pressure. Pressure, if I increase pressure, this gets really interesting. If I increase pressure, I can sometimes force one element into a space that it wouldn't have fit in otherwise. If temperature is very high, the atoms are moving faster, and when they move faster, they create larger spaces between one another, and we can force some larger atoms in there with higher temperatures. So crystal structures, if the temperature is high, the atoms are moving faster, there's more space, they're more open. So now larger atoms can fit in. They don't need that 15% size difference. And they can replace each other better. So this here is this plagioclase or feldspar solid solutions. In a high temperature, it's easy for them to replace along here. If we drop the temperature, now orthoclase and albite will not replace one another as easily, and even along the albite to anorthite, they won't replace one another as easily. This miscibility gap becomes larger when the temperature drops. The miscibility gap gets smaller when the temperature rises because it's easier for them the atoms to replace one another. When pressure is high, high pressure can change the size of spaces inside of the crystal. So a larger ionic radius can be pushed in. Okay, so I had to take a long break because my computer was acting strange. So we're just going to start up with the next bit of the lecture, which is all on the silicates. We're going to learn what the silicate minerals are. And again, this is 92% of all the Earth's surface. This is what we're living on. It's the most important type of mineral, and it plays a large role inside of the Earth. And for us to understand igneous processes, these are the minerals that we need to understand. So in the grand scheme, that 8%, we probably won't get into them. We'll probably just focus on the silicates. Today we're going to learn about their structure, how they're formed, what types of minerals they make, and mostly it's just about shapes. So and a little bit of chemistry. So we're going to see how this goes. All right, so again, silicates, 92% of Earth's crust. Made of the 8 most common elements in Earth's crust. Tell me, what are they? I wish I could listen to you. What are the 8 most common elements in Earth's crust? Remember. Oh, see Alfie, Knack. So these elements are going to be the most common elements in the silicates, and the silicates can have other elements in them, but they are mostly made of oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. We often call these, if I had my book, which you haven't read the book because I lost the file and I cannot find it. So you've not had to read it. But these are what we call the common rock forming minerals. Why are they important? If I was going to be teaching you each of the types of minerals, we'd be getting into this more, but they're used in brick, stone, cement, glass, made silicon chips. You cannot remove the metal from a silicate. These are industrial minerals. Can't remember if you had the mining class with me or not, or mineral tech, mining. I don't know if you had any of the mining classes with me. I've forgotten. But these are the types of minerals that, you cannot remove the cation. You cannot remove the metal from these minerals. So they are not generally used. They're not the mined minerals, not what we're going after in the mines. They're just used for things like gravel and cement and things like that. All right, what are the silicates? So a silicate is one or more silicate tetrahedron. Tetrahedra is actually plural. Bailey, are you itchy? Come here. You're making loud noises. One or more silicate tetrahedron linked together. So a silicate tetrahedron is this shape. I want you to learn this. I want you to be able to draw this for me and explain it. And it's SiO4. Okay, so we looked at this before when we were talking about unit cells, mineral unit cells. We've got, in this case, we've got 4 oxygens. So these are each an oxygen. And then on the inside is a silicon. This is a structurally stable anion group, so it can be used just by itself, SiO4. Or it can start to build things, and this is where it gets interesting. We can arrange these little tetrahedron in different shapes to create different types of minerals. So this is a different type, this is a different type, this thing here is a different type. They're able to form polymers. Maybe I've taught you polymers before, but a polymer is 2 or more shared groups of ions of the same type. Let's see here. I don't think you need to know this part. The charge reaching the silicon atom is half the charge of the oxygen. Don't worry about that part. I don't think that's going to be important. Poly, I don't know why I don't have poly over here. Poly equals many, and mer means parts. So a polymer has many parts, just groups of these silicate tetrahedron. Polymers can be organic too. Actually, normally when you hear the word polymer, you're talking about organics. How do silicate minerals become stoichiometric? All right, what does stoichiometric mean again? It means that whatever the formula is, that the charges on here, oops, these will be positives over here and these will be negatives, whatever, that they're all going to equal 0 overall charge. So how does a silicate mineral become stoichiometric? And silicate minerals want to be stoichiometric. I'm 99.9% sure these are all stoichiometric. How they do that? They share oxygen between the silicon. So where is the oxygen again? Whoops. These are the oxygens. So these oxygens can be shared. Look, right here, that's a shared oxygen. Right here, those are all shared oxygens. So they can become stoichiometric partially by sharing oxygens, which link the tetrahedrons together. And then they can add cations. So this is an anion group. If it's all by itself, or if it's making this, it's fine. But if it's well, actually, if it's all by itself, it's not fine. When it's all only attaching to itself, it will be stoichiometric. But if it's by itself or making chains or making rings or plates, then it needs other things. So it's not just going to be the tetrahedrons. It's got to have some other positive cations that attach to it to make it become stoichiometric, with zero charge. So the silicate minerals are classified by their structure. And this is very, very useful because structure, as we found out in the last lecture, structure has to do with temperature. So the higher the temperature, we have, if very high temperatures, we have simple structures. Very low temperatures, we have more complex structures, again, because those atoms are moving so much around. Somehow you did a really good job answering that last time. So let's look at this. Where do you think, oh, so structure is controlled. It says here controlled by the ratio of silicon to oxygen. I shouldn't have written it that way. That's not quite true. Structure is usually actually controlled by temperature. But you can see the structure based on the silicon and oxygen ratio. So here we've got 4 oxygens to 1 silicon. Here we've got 7 oxygens to 2 silica, 3 oxygens to 1 silica, 6 to 2 or 11 to 4, 5 to 2, and 2 to 1. Oh, my question. Let's see here. Am I going to get ahead of myself? I might be a bit getting ahead of myself, but that's okay. Where on here, let's looking at these structures, which of these look like it's the simplest structure and which looks like it's the most complex? So here you've got just one tetrahedron. So this is very simple on this side. And these are all, this is just totally all combined together on the right side. So this is complex. So where do you think the highest temperature is in the creation of these minerals? Where's the highest temperature happening? It's going to be wherever you see the simplest structure. So here, temperature is high on this end. The more complex it gets, that means the temperature is decreasing. All right, so we're going to start off with the nesosilicates. The nesosilicates are made with just a silicate tetrahedron and 1 or 2 more cations. So the best example of this, we've already looked at it, is olivine. Olivine can be made only with magnesium. It can be made only with iron, or it can be made with a combination of magnesium and iron, any combination. Interestingly enough, we're going to get, I think it's, I have to think for a second, I think it becomes more green. This is not important for the structures. It becomes more green if we've got more iron. It becomes more black if it has more magnesium. I think iron's more dense than magnesium, so it becomes more dense that direction. All right, so neso, roots are going to help you memorize these. We're going to use roots, all right? Not every single one of them I think has roots, but maybe they do. Neso means island, all right? Think about Hawaii or something like that, Sri Lanka. Just a little island all by itself, all right? So the nesosilicates are just this small little, not complex, very simple structure. Oops, that's all right. Next, silicates are double tetrahedron sorosilicates. We've got two pyramids attached to one another. And the best example of this is epidote. The silicate end is going to be Si2O7. So 2 silicas and 1 oxygen. Over here it was 1 silica and 4 oxygen. You don't have to memorize that if you memorize the shape. If you memorize the shape, you'll see 1, 2, 3, 4 silica, and on the 4 oxygen, and on the inside there's the silica. Over here we've got 1, 2, 3, 4, 5, 6, 7 silica. I just did the same thing again. 1, 2, 3, 4, 5, 6, 7 oxygen, and on the inside of each of these is a silica. So 2 silica and 7 oxygen. I don't have a root for sorrow, apparently. I don't remember having a root for sorrow anyway. The cyclosilicates, or cyclosilicates, make a ring. So that's a ring of 3. This is a ring of 4. This is a ring of 6. They're going to have a ratio of 1 to 3 silicas to oxygens. So let's see here. It can be 3 to 9, 4 to 12, or 6 to 18. So we'll just look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygen, and on the inside of each of those is a silica. Can't believe I can actually draw that small. That's cool. Ooh, is it still recording? Why did it freeze? There we go. Is it recording? Yes, it's recording. Good. And a good example of that is beryl or emerald. Ooh, this is important. I've been missing this. This is super important. These are going to come in soon. This is an ultramafic mineral. So if you remember on our, I should have thrown this slide in here. It's all right. If you remember on our igneous rock chart, we have ultramafic minerals or composition. We've got mafic composition, intermediate composition, and felsic. This is going to get really, 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 really important. So nesosilicates tend towards being ultramafic, tend towards it. Sorosilicates tend towards being mafic minerals. Cyclosilicates tend towards being an intermediate mineral. And cyclo here means circle. So it's making a loop. A loop of tetrahedrons. Inosilicates make a chain, and they have a, depending on which type of chain, they can make a single chain or a double chain. So they could do a 1 to 3 ratio, or they could do a 4 to 11 ratio. I'm not going to count that out because it starts getting complicated in here. Augite is a good example of that. Let's see here. In this case, I think this might be the first one that's got the aluminum. Yes. Once we get up here, aluminum, interestingly enough, can start switching out for silica. But you can see here we've got 2 to 6, which means that it's a 1 to 3 silica to oxygen ratio, and that's only because the silica and the aluminum can take their places there. So 2 to 6 is really 1 to 3. Augite is an example. This is a mafic to intermediate mineral depending on what atoms, what cations are attaching. Oh, I've not been talking about the cations. Go back, Carrie. Go back. Well, I sort of did. These are cations over here, right? These are positive elements here. These over here, this especially right here, is positive calcium. I think that's 2 also. The iron is positive. So these are our cations. In beryl and emerald, the Be, Carrie, what is it? It's positive 2. So these are all cations, right? I'm not going to give their numbers because I don't have them all memorized, but these are all cations that are attaching to the anion group and making it all stoichiometric. Ino, for inosilicates, again, it's a chain or like it's a line or a double line. And ino means hair, so think of a piece of hair or 2 pieces of hair making a line. A phyllosilicate is a ratio of 4 to 10. I'm not making you guys memorize these ratios. That would be ridiculous. I want you to memorize the shapes. I want you to be able to recognize the shapes and say, that is a phyllosilicate. That is an inosilicates, all right? So a phyllosilicate, the best example of this one is muscovite. It's that flat mineral that you can peel apart. It's made of layers. And actually, this whole thing down here is going to be our silicate group. It's got a hydroxide on it, which makes it a little weird. So it's actually kind of just this part, but it's a little strange in there. Phyllosilicates. Phyllo means leaf. That, again, you can peel these right apart. It's just one layer of molecules, and then another layer of molecules, and another layer. These are the kinds that are held together by van der Waals bonds. And so that's the phyllosilicate. That's the root there. And last of all, we've got tectosilicates, and there's only one. No, that's not true. There are more than one tectosilicate, but they're the SiO2 group. One silicate to two oxygens, and they're just continual bonding. Oh, that's actually pretty good, to itself. So this is the silica, and each of these big ones is an oxygen, and they just continually keep bonding to each other in a really large structure. And tecto, you remember what tecto means? Tecto, we had this root before. Oops, hello, come on. Oh, no. Tecto means to build. It's just building and building and building on itself. So tectosilicate is a complex, the most complex of the silicates. All right. So this is basically how we're doing for silicates, is just learning their structures. So what do we have right here? The simplest structure. It's very small. Think about islands. This is going to be a nesosilicate. And then here we've got a double, and that will be a sorosilicate. I don't have a meaning for that. I don't know why it's called soro. Sorry. Here, these three, we're making circles. So these are cyclosilicates or cyclosilicates. I'm not sure how you pronounce it. CYCLO. Neso, soro, cyclo. This is a chain or a double chain. These are inosilicates. This is making one flat piece. If you've heard of graphene, graphene also would be considered it's not a phyllosilicate because it's just made of carbon, but it does the exact same thing. It makes one big flat piece. And so phyllosilicates, oh, spelling, L, is it two L's or one L? Does it say down here? It does not. I'm not sure. I'm going to put one L because usually when I think there are two, it's only one. Phyllosilicates, phyllo meaning leaf. Think of a leaf, one flat leaf made of all that same structure over and over again in 2 dimensions. I know. Oh, it's going to tell me phyllo right there. Yay. And what's this last one? Large complex structure built from many pieces of, from many tetrahedrons. This one is the one that's built. It's tecto. I'm not even going to write because it's going to show. All right, so nesosilicates. Seriously, all I want you to really be able to do is learn the name and match it to the structure. Really, that's it. Nothing more than that. I did not teach you TX diagrams, or I'm not teaching you this. This is very interesting. It's great for your brain. You're not going to learn it from me this year. I'm going to just jump all through here. All right. I think I might be at the end of this lecture. I've mentioned before that temperature can affect solid solution. So we're just going to jump past that. And that's it. All right. So there we go. I'm going to put some notes in there on what I want you to give me for videos. And yeah. Good to see y'all, at least in your videos. I'll talk to you soon.